And this is the part one where we are looking at the beginner section. And this is for complete beginners who haven't used SQL at all in the past. And this is the video for you. And within here, we are going to look at a few topics. And this is a sort of a roadmap or a framework. And you can follow this framework on your way to mastering SQL and beyond. So this is all the beginner section, and in this section we are going to look at the introduction to SQL and databases, relational databases, NoSQL databases, and etc. We have some basic manipulating data and querying techniques over here, SQL structure and syntax, and some ways of joining tables together, and also more importantly basic database design as well, which is quite important because when we are learning SQL, it's also very important to learn about how to optimize or how to design a database and how to optimize the performance of the queries and other things as well. And this will give us a good solid foundation on SQL and database. And next section we have all of this, which is all the intermediate stuff. And here we have some advanced querying techniques, a bit more of data modeling design and transactions, performance management, and advanced data types, and all of these things. And within all this, we are using BigQuery data warehouse to run our SQL queries because it's very straightforward and easy to get up and running. You don't have to spin up a database or have any special code editors on your computer. We can get started by just signing up to Google Cloud Platform. And then eventually we will move on to advanced topics within the video, and that will be part 3, a separate video as well. And here we look at some complex queries and database administration, warehousing concepts, emerging trends, NoSQL, new SQL, so on over here, and BigQuery in different environments, analytical functions, window functions, and all of those kind of things we will look at here. I've said mastered SQL for now, but of course it takes a lot of practice in real world to get to this stage, but at least we have a good foundation by all these videos and topics that we can go out and venture into the world and start playing around with real data and continue on our journey. So let's start with a quick introduction to what SQL actually is. So SQL actually stands for Structured Query Language, and it's primarily used with relational databases, and it's used with a lot of different relational databases like we are going to see in a moment. And it's widely used so much because of its simplicity and effectiveness in handling a lot of structured data, particularly in relational databases. Now let's look at some of the key features of SQL. I mean, most of these you don't have to understand it at the moment, but we'll still list it over here. So as we do progress in the course, you can reference this video back and understand where these features are fitting in. So the first feature is actually a structured format. It's very easy and simple to understand once we get a hang of it, and it's very easy to follow, and the learning curve is not as steep as would have been for some other technologies. And it's also very universal, like it's used with MySQL database, Postgres, Microsoft SQL Server, BigQuery, and so many other databases as well. And the key thing about SQL with all these databases is even though the core structure and the syntax is same, some of these databases might have their own twist added to SQL, like we're going to see with this BigQuery SQL in a moment. And of course, there are also these data manipulation, data definition, and data control, and all these are like the core features of SQL. So data manipulation is it allows you to insert, update, delete, retrieve data like it has to because it's a database, and the primary function of this database is actually we want to interact with it, and the way we do that is by insert, update, delete, and retrieve data. There's also data definition, which allows us to use SQL to modify the structure of the database, like the tables and so on, which we are going to see in a moment as well. And of course, there are data controls where you can define access control to who has access to data and so on as well. Now let's move on to BigQuery because that is what we're going to be using majority in this series because BigQuery is very easy. It's out there. You don't have to install anything. You just have to sign up to Google Cloud Platform, and then we have access to BigQuery where we have data sets and other things, and we can get started with learning BigQuery SQL. So let's understand what BigQuery actually is. So BigQuery is a serverless, highly scalable, cost-efficient multi-cloud data warehouse, and it's designed for business agility. And even BigQuery has a variant of SQL, and it's called the standard SQL. And it's called BigQuery SQL because it has some extensions and modifications for compatibility with BigQuery's architecture, right? So when we think about databases, what does it actually mean? A database is just a collection of tables. Now, that's how I like to think. There might be other NoSQL databases and other things which we're not going to consider at the moment. We'll just stick to relational databases. And imagine this is our little table with all this headers. We have ID, name, age, city, and we have all the data. Think of it as a Google Sheet or an Excel file, right? Now, how do we go about creating this? Is using this query that we have here. We'll go over what each of these mean and understand what the syntax of SQL is and so on. But for the moment, this is an example of how we will go about creating a table within BigQuery using SQL. So I would like to summarize this introduction video by saying SQL is a powerful language for interacting with many types of databases, relational databases out there. And it's famous because of its simplicity and effectiveness. And in this series of video, we are going to be using BigQuery. BigQuery is a data warehouse where we can analyze a huge amount of data. So far, we understood that SQL is a structured query language used to talk with relational databases. Now let's understand what a relational database is. So a relational database are a type of database that stores and provides access to data points that are related to one another. Now that was quite a lot. So let me just quickly jump to an example table and this will make a lot of sense. So here I have two tables, customer table and orders table. Now the customer table has customer ID, name and email. Orders table obviously has all of this, but then you'll notice there is also customer ID. Now this customer ID is exactly the same as this customer ID from this table. And that is how we can join these two tables together, right? And you might ask, why do we need to join these tables? So let's take an example. So in this order table, imagine we have this order ID and we can get all the orders that a customer has ordered. Now, but the ID is only customer ID, which might just be a set of numbers or string alphabets or whatever it is. But if we wanted to get like the name and email address of this customer, we don't have all that information in the same table. So imagine this is our one sheet, like a Google sheet where we have all these columns. Now imagine this is another sheet, right? So if we want to get the name of the customer and the email address, we have to join these two sheets or tables together. And the way we do that is we have a common column here in both these tables, and then we join, and then we have two more columns added over here, which will be the name and email. So we'll get the name and email over here. Now, that was quite a lot as well, I understand. So let's go over what are the other aspects of the relational database. So a relational database has a few key components. And the first one is obviously a table. So imagine Google Sheet, that is your table. And within that sheet, we have columns and rows. And within these columns and rows, there's something called as the primary key and the foreign key. Now, the best way to understand what these two primary and foreign key mean, a foreign key, think of this as just a serial number that keeps on incrementing whenever you add new rows of data. So in your Google Sheet, you have a column which is just the serial number and they're all unique. So that is a primary key and this is unique and this exists on all the tables. Now, there is this foreign key, which is quite interesting. And in the example that we saw, where we were trying to join the two tables with the customer ID here over here, this is the foreign key, right? So customer ID over here would be the primary key of customers table, where this would just be the serial numbers of all the customers over here. And then this table, this column is actually referenced in orders table, and this would become the foreign key. Again, when we get to a more intermediate lesson on entity relationship diagrams, these are the things that will be easily understood in that lesson. But over here, try to understand that there is a primary key, which is the order ID and the customer ID. So the order ID is a primary key for orders table and customer ID is the primary key for customers table. And then of course there is this foreign key, which is referencing this customer table. So these are components within a relational database. Now that we've understood that, let's actually quickly take an example of how we are going to create these two tables, these DAX and other things. We are going to look at it more detail in future, but here this is a query that will just give us what we want with is these two columns. Now, when we spoke about primary key and secondary key, here is a good example. So here, this is straightforward. There is a create table and we are creating the customers table. And there is also data set. That concept is specific to BigQuery, and we'll get to that in a bit. But here we have all the columns listed, the customer ID, name, email, and here we're saying customer ID is the primary key. And we also have a second table over here, which is the orders. And here we have order ID, date, and other things where we want to put specific attention over here, where we say order ID is the primary key for this table. But then there is a foreign key called customers. And let me just bring this in view here. So there is a foreign key called customer ID, and that references the customers table. And within the customer table, there should be a field called customer ID. That is what it's referencing. All this is doing is it's just referencing these two together, so that whenever we say customer ID over here, it knows that we are referencing the customer table. So that's all about relational databases, the basics of it at least. This should give us enough understanding to write some basic SQL queries. That's going to come next. Next, we have something called the DBMS, or database management system. So a DBMS is actually a software designed to store, retrieve, define, manage data in a database. So basically, it's a software that we use to interact with the database, right? And SQL is the language that we use to interact with this software. And it provides programmers with a systematic way to create, retrieve, update data, and manage data. And let's look at the type of DBMS. Now, I like to think of DBMS as just database, and that makes it a lot easier to understand. Now, there are various types of databases. The first one is relational databases that we've been seeing so far, like the MySQL, the Postgres, and so on, which are the examples again over here. There is also something called as a NoSQL database, where instead of storing data as tables, columns, and rows, we just store everything as a document, and we just keep appending to that document. Now, there are various scenarios where we might prefer one over the other, and that is again depending on the application that we are using the database for. But it's good to know that there are two different kinds of databases, primarily NoSQL and SQL. And for NoSQL databases, we obviously have the popular ones, the MongoDB and Cassandra. There is also in-memory database, which stores data mainly in memory, and the best example of this is actually Redis. So instead of storing all the data on disk, everything is stored in memory. So this is helpful for caching and other things, where the latency between giving an instruction and getting that data back is very, very small. It's because everything, all the data just lives in memory. So Redis is a good example there. There are also column-based databases and also object-oriented databases. So a good example of columnar database is actually Apache Cassandra, where all the data is stored in columns instead of rows. Again, there are various examples where this might be beneficial. The best example is when we're doing analytics, where we are querying a lot of rows. So in that case, instead of querying the entire table, we are probably just interested in one or two columns within that table. So it makes sense to store all of this in a column format. Again, if this was a bit too much, we'll go and look at specific examples in a bit. But understand that there is a way for storing this data as well. So there is obviously storing it on the disk or in memory, and then there's a way of storing it as a row or a column. And of course, there are these object-oriented databases where data is stored in the format of object. Now, when we talk about DBMS, database management system, now what are its characteristics? So we have some of the characteristics written up here. So that is, the first one is data abstraction, right? So regardless of how the database is built, if the data is being stored on disk or in memory, or if it's row based or column based, whatever it is, it abstracts away all of that. It just gives a SQL and other things that we can interact the database with. So database management system is primarily used for this. And then there is also data independence. So where modifying the schema at one level of DBMS does not require changing schema at next higher level. Again, at this level, when we are just beginners, we are starting off with all these things. It's good to keep in mind that these concepts exist. But again, I would encourage you to come back to this section at a future date and revisit all these things, at which point will definitely make a lot more sense. And we have efficient data access, data integrity, and backup and recovery. All these things are taken care by the software that runs on top of the database, and that software, we are calling it as database management system. Again, a quick note on BigQuery as a database management system. So BigQuery, as we saw, it's fully managed and serverless offering by Google Cloud Platform. And we'll get to the actual UI and interacting with BigQuery in the next section. But let's just understand what all the critical details right away. So it's a serverless data warehouse that is part of Google Cloud Platform, and it's designed for very, very large scale data storage and analytics, can handle petabytes of data, query against them. It's serverless, so we don't have to worry about the compute instance, how much memory or how much time it's going to take for these queries to run, unlike in some of the data warehouses. But if it's all serverless, it's all taken care behind the scenes, and we just have to focus on looking at the data, querying data, and building our analytics or reporting on top of it. And of course, it comes with data security. There's a special interface as well, which we are going to be using for interacting and building our SQL queries. Now, because we are going to be working with BigQuery so much, let's understand all the nuances involved in using BigQuery. So we already know that BigQuery is fully managed, serverless, highly scalable cloud offering by Google Cloud Platform. And let's look at some of the key features of BigQuery. So again, it's a serverless architecture, and BigQuery really abstracts away all the complexities behind BigQuery, and it just provides user with a service where they can just input data and analyze it. BigQuery is also very scalable, and it can scale to, as we saw, petabytes of data, which is quite a lot of data. And it gives us a nice, smooth SQL interface, which we are going to see in a moment, where we can write SQL query to interact with our data. It's all about performance when it comes to BigQuery, and it's built for speed and performance as well. And BigQuery also comes integrated with machine learning. And although we're not going to be using too much of machine learning in this course, I'll probably have a separate version or a separate course or an add-on or an update to this course where we look at a lot of BigQuery machine learning. BigQuery is also big on data security, and it's obviously cost effectiveness is huge as well. And this comes into play if you're comparing this against Snowflake or Redshift or other big data warehouses out there. Now, to really understand the BigQuery ecosystem, or how all the tables and columns and everything is organized, we have to understand what's really happening under the hood in BigQuery. So let me just pull up this drawing over here, and we can see that in the outer circle we have the BigQuery, which is encompassing everything. And if you go a level deeper, what we have is a data set. Now, think of data set as database actually, where this can be all the data that you have from, let's say, your e-commerce data, or maybe this is a database where you have all your ads data or your supply chain data or finance data, whatever it is. So this is just a logical division between the kind of data that you want to store within BigQuery. And within this data set, we have all these tables, right? So this can be the e-commerce customer table and maybe the orders table and so on, which we saw in the first video. And these tables are just rows and columns, and think of these as Google Sheets or Excel or whatever you have. So again, just to reiterate, for going from the inside to out, we have tables, and a lot of tables make up a data set, and a lot of data sets make up what we have is BigQuery. So that's what we have here. I've got this written down over here. So dataset, they contains table and serve as a top level container in BigQuery. And of course, tables are the places where we store all the data, the rows of data, the columns of data, and so on. And there are also jobs within BigQuery. So querying data is a job, exporting data is a job, loading data is a job. So all the actions that we perform, they're all called jobs. And within Google Cloud Platform, they're all organized as projects. So these are logical divisions of the kind of things that you want to have on GCP or Google Cloud Platform. And these projects all have their own BigQuery, have their own resources, have their own billing setup, and so on. And we're going to look at all these things when we do actually get to the user interface. But let's quickly look at how to go about creating a data set. So again, if you remember, data set has a collection of tables within it. So it's very simple. We say create schema my data set. Now imagine within this data set, we want to put some tables in here now. So the way to do that is by saying create table, and we specify our data set, which is exactly the same as we have here. And then we specify the table. So this could be orders table or customer table, whatever it is. And then we specify all our columns over here, right? So we have ID, name, age, and city, and then we have the type of data that it's storing. And we'll get to this part in a bit, in a few more videos. But it's good to know that this is how we want to write a query, and this is the proper syntax of creating a table within BigQuery. Now that we know that we are going to be using BigQuery quite a lot, it's also beneficial to understand the architecture and some of the intricacies of BigQuery. So let's first start with the storage. Now, initially we saw that there are different types of databases or database management system where data is stored on memory or on disk, or it's stored in a row format or a column format. But here, BigQuery actually utilizes column storage format. And this is a lot better because of the application that we are going to be using BigQuery in, where we are querying petabytes of data. And it's beneficial because we are mostly using it for analytic purposes. If it were transactional data, then a relational database or a row level data storage would be perfectly fine. But because we are running analytics where we are only concerned with one or two columns or maybe few columns, and we're not bothered about all the rest of the columns within the database, it makes much more sense to just have everything stored in a column format. And that's what BigQuery uses under the hood. Now, it's also built on Dremel query engine. At its core, BigQuery uses Google's Dremel technology. This multi-level execution tree turns SQL queries into execution plans and distributed across thousands of machines in parallel. And we don't have to worry about all these things yet. But if you're interested, you can go in and check out the detailed architecture. But for our purposes, where we're trying to learn SQL, these things are perfectly fine as just a snippet of information. Now, again, what we saw, it's a serverless model. So it operates in a serverless fashion where you don't have to spin up any servers or anything. It's all there. You just have to load data and start querying it. BigQuery has a separation of compute and storage. And the way we pay for using BigQuery is we pay for the storage and the compute resources that we use to query the data against the stored data, right? So we'll get to that bit in a moment as well, as to how we are built when we use BigQuery. And it also is very good because it integrates really seamlessly well within its ecosystem of other tools in Google Cloud Platform. So if you want to import export data or to Google Cloud Storage, that's possible. Data flow, if you want to load streaming data or batch data and do some ETL processing, that's very well integrated as well. And there's obviously the AI platform for advanced analytics and so on. So what are the really big advantages of BigQuery? So first of all, it's the speed and performance. Because of its Dremel technology and column storage, BigQuery is can handle large amount of data quite fast, and it's really scalable because we're not worried about all this compute instance and so on. It's all serverless, so the scalability is happening seamlessly in the background. And of course, the ease of use is quite good because it allows us to do SQL queries and so on. And it's also very cost effective because we are not paying for spinning up servers and so on. We're just paying for what we use. So we are going with the pay as you go model. And it makes it much more efficient. And even when we're running queries, like we'll see in a moment, we'll actually get a preview of how much data we are querying, and based on that you can estimate kind of if it's going to be a large query which is going to cost a lot, or if it's going to be a smaller query which won't cost that much. And of course, BigQuery is huge on compliance and security with standards like ISO, HIPAA, and all those robust features. And it also has integration with advanced analytics like machine learning, like we spoke about. There's also geospatial analysis, and it also integrates really well with business intelligence tools like Luca Studio and actually most of the business intelligence tools out there. So let's start to understand what this SQL structure is and how we can start to write some of these SQL queries. So there are a few key components that we have to understand within SQL. So to keep things very simple, understand that there is a basic select clause within the syntax of SQL. We're specifying what are the columns that we want when we read the data. So imagine there's a customers table. So if we want to specify, we need the name and the ID of the customer. That is where we specify. And the next in line is we want to specify where we want to read this data from, what table we want to read this data from. So that is where we have the from clause. And we do also have other statements over here, which we'll look at a later point when we start looking at the examples. But this is the basic structure of SQL, where we are saying select the columns from the table. And then there are a few expression, predicates, queries, and commands, which we'll come to in future videos. Now let's look at a simple example of how this looks like. So we have the select over here, select statement. And this is again specifying what columns we want. And then we have the from statement over here, and then we are specifying the table. And we also have these two, which is the conditions. And we'll get to this in a future section as well, where we can specify, okay, give me these two columns, but then just give me this person, right? And that would be a where clause. And then maybe if we have like, we want to get the orders of, let's say, yesterday, and when we specify where the date is yesterday, and then we can specify how we want to order this, maybe give it in ascending order, descending order. All this we'll look at in a minute. But let's first look at an example. Now, in this example, we are mostly concerned about this, where we are looking at the select data from. But because we are starting fresh, we also want to have some table and data within it so that we can run this query, because otherwise this query will return an error or says that there's no results for this table, right? So we are going to run these two queries, initial queries, and you don't have to worry about understanding these two queries yet. And we will look at these in a future section where we have dedicated section for create clauses and insert clauses and so on. But for the time being, we'll just run these two and have some test data in our database or in BigQuery, and then we'll run this. But let's jump into Google Cloud Platform, go to BigQuery, start to understand the layout of things over there, and then we'll come in and create these two tables and run our basic query. So here I am in the console of Google Cloud Platform. If you're new to Google Cloud, an easy way to sign up would be to come to console.google.com, sign up for Google Cloud Platform. I believe there is a free trial as well that Google gives. And once you're signed up, you would go and create a project. And once you're inside the project, which is listed over here, if I just click on this drop down, you'll have a list of all the projects. Now I'm selecting my project called SQL course. And if you search for BigQuery here, the first option that we have here, data warehouse and analytics, if we click on that, we will end up on the user interface that we were just on in this tab, which is all this. Now, when you have a project over here, so I have this SQL course 406909, which is my project ID. We'll have this project ID show up in the sidebar over here. Ignore all these two; these are from other projects. But in our case, this is the project that we have. And to create a data set, we would come in here and click on create data set. I'm just going to call this SQL, and we leave it at multi-region. US multi-region is fine. There are a few other options which we don't have to worry about. I'm just going to say create data set, and then we'll see we have some of these data sets up here. Now, as we saw in the previous video, there is a project within BigQuery, and within that we can have several data sets. Like this could be like ad data, and then this could be like Shopify or e-commerce data and so on. So we have a logical grouping called data set, and within that data set we will have several tables. So if I go back to my notes over here, so we want to create a table and then we want to insert this as well. Now, again, don't worry about all the syntax, but what we'll do is we'll just copy this, and I'm just going to create a new tab over here, and let me just paste this. If we have this my data set, I'll just write SQL because that is the data set that we have. And then within the data set, there will be a table called employee, and this is the schema for the employees. Now, we also have this tick mark, green tick mark over here, which means Google is happy with to run this query for us. So when I hit run, this query will run. So let me just collapse this. And it says the statement created a new table. That's great. So if I open my sidebar up, so I'll see this employee table over here. Okay, let me just do that. Okay, we have the employee table over here with all these columns that we can add data to. And then if I click on preview, we'll see there is no data. So let's add some data into this. So I'll just come into here and then copy this. And then let's go back into the same. And here again, we have to change our data set. So let me just do this. Actually, we can delete all of this for now. So we want to insert data into SQL dataset into the table, and these are all the values, and then we can have this run. So once this is finished running, we can come into the employee table again. And if I click on the preview tab now, it will load up few values that we have. Right. So we are good to go with the employee table. We have some test data over here. So let's go back into our notes and then see what exactly we want to run. So we have the select statement over here, and we just want the name and position from this data set. Let's try to do that. So if I come into here, I can just say, so let me just copy this section over here first before we run the where clause. Let's just run a basic statement. So I'll come in and paste this, and instead of my data set, I'll just say sql.employee. And if I say name and position, if I run this now, let me collapse this. So we'll get the name and position of all the rows from our table. Now, in our example, we want all the employees who have a salary greater than 65,000. So if we look at this now, we have only Alice, who will be the developer whose data we can get. So again, a way to visualize this is the table we've just created. And if we want to get only this person with a salary of 65,000 and greater, we can specify that. So let me just copy this. And if we go back to BigQuery, I'll just add another line over here. And then if we hit run, so we'll only get one user who is Alice. And if you want to get all the columns instead of just getting name and position, I can just do a star. And if I run this now, we'll get all the columns. Within we get Alice. What was the other user? Bob with 60,000. So if I change this to 60,000 and run, we'll get Bob. And of course, if we just do greater than equal to 60,000, we'll get everyone, including Bob and Alice. So there we have it. We have both the users and we've run a basic select query from our table. Now in the future, when you do encounter any table, so this is how you would run it. But there is one advice that I would like to give as well. We can use a limit clause and then specify the number of rows. So whenever you come across a new table, just select a few tables first, investigate the schema like we did, come into the schema section, try to understand what the schema is, because if it's a particularly large table, then you might end up querying a lot of data, which might cost money. So we generally look at the schema and then try to get that. And when we do get all the results, just try to limit to number of columns. So here, if I just say, I don't want everyone, but just give me one person, and then it will give me just one person from the table. That's just a quick bonus, if you will. But we look at all these clauses in a much more detail. Let's start looking at the basic data types that we have within BigQuery. And if you remember in the previous video, we had a create statement where we created an employee table. And within this table, we specified a few data types like int64, string, float, and other things. So let's understand what these actually mean. So there are various data types within BigQuery, and then there are these numeric data types like int, which is for integers, 64-bit integers. There are these float data types if you want to specify like a floating point number or a decimal point number. There are these numeric and big values and other things as well, which we don't have to worry about yet. And for now, I think int and float is the most common use case. There is also Boolean if you just want to have a true or false values. There is a string type where you can store like usernames, addresses, and other text fields. There is also bytes data, and we also have date and time types. So if you want to order by purchase date and so on, it has to be in a date format. So BigQuery can understand that it is a date time format or a timestamp format, and it can order it by those columns. So within here, we have just the date time, and then timestamp. And there are some intermediate and advanced level types as well, which is like a record, which is think of it like JSON type of data. And there is also an array. And if you don't understand all this, don't worry about it yet. We'll come and look at this in detail. So array is just a collection of values and so on. And you can have all this in just one column, and then you can run queries on this. So we have the structural types. So these are the basic types within BigQuery. And again, where we would use this is when we are creating a table or specifying the schema. So if I go back into my UI here again, instead of creating this using SQL, you can also come in here and then say create table. And this is another way of creating tables manually. You can give the table name and project, and you can also define the schema over here, which is where you would put in the field and then the type of field it is. So let's say this is the name of a user. I can click and say, okay, I want this to be string. And then maybe there's a purchase date. And for this, I want this to be a timestamp and so on. So this is where you would define a schema. So these are the basic data types within BigQuery. There might be a few minor changes between database to database, but most of them will have all these basic data types anyway. Let's understand a bit more about the actual table structure within BigQuery. So as we know, tables are the fundamental elements where the data is stored in BigQuery. Now, there are specific characteristics of these tables. So first of all, if we consider table structure, the table structure itself has a schema defined. So it's not like other NoSQL databases where you can just dump data without schema. So in BigQuery, we have to define a schema where we define the name of the columns and what data type that column contains. So that is the basic table structure. And it's also possible to have nested and repeated fields due to the nature of BigQuery's handling capabilities. And when we say nested and repeated fields, so these can be like JSON data or array of data. and array of JSON data and so on, which are some intermediate level SQL queries, which we'll look at a bit later stage. So those things are possible within BigQuery's table structure. Now, to understand the actual types of data, so there are two types of table types. There is the native type, and then there is also external tables. So the native type is actually where the data is actually stored internally in Google Cloud. So that makes sense, right? So it's called native type. So it's stored on Google Cloud, the data. And then there are these external tables where you can link tables to external data sources like Google Cloud Storage or Google Sheets and so on. So these would become external tables. And this is another type of table that we can have within BigQuery. Now, another very, very important consideration that we have to think about when we think about these tables, no matter what kind of database we are using, is how we can do partitioning and clustering. And this is for mostly performance improvement. Within BigQuery, we have partition tables and clustered tables. So again, we'll have a specific section on all this in the future video, but let's understand all these things do exist within BigQuery. We can partition tables by dividing a table into segments, often by date. So imagine you have customer orders coming in every day. So you can have a partition table where you can create partitions for days or weeks or months, whatever you want. And when we do queries, we can just select that partition. Again, we'll go through this much more detail at a later stage. And then we can also have clustered tables where we can organize data based on contents of one or more columns, which can improve the query performance again. And we can also understand the data set as well. What is this data set or this logical grouping where a data set can have a lot of tables within it? So BigQuery's dataset acts as a container that holds a lot of tables and views. And up to this point, we haven't really touched upon views yet. We are still sticking with tables, but we'll look at that in a moment. And there are a few characteristics of these data sets as well. So a project can contain multiple data sets, and data sets can have a lot of tables within it and can be shared across projects as well. So if you remember in our SQL course project that I have created, so if you have another project called Stella Hey Stella, like over here, this data set can be shared across these two projects. Again, we'll look at all these things, sharing, governance, security, all these things at a later stage. We can also have access control at the dataset level that determines who can access the tables and views within it. So imagine if you have HR data or some sensitive data that you don't want to give access to everyone on in your department. So you can have specific access created just for HR people who have access to this data. So that is access control. We can also specify where this data set is located. So when we are creating a data set, you can specify the location, and this location is where BigQuery is going to store the data, and the location can affect query performance and data availability as well. For instance, you can have multi-region, which is what we created initially. So the data will be replicated across multiple regions in the world, or you can just specify one single location, let's say US East or EU West or something along those lines. So those kind of things are possible. Again, just to revisit, we have schema. So if we think about Google Cloud Project, these are the projects that we can have. We can have numerous number of projects. And then within that, we can have data sets, which we can have multiple data sets within a project. And then within those data sets, we can have multiple tables with multiple rows and columns and data types and so on. So this is a very quick introduction look at the tables and data set structures within BigQuery. In this section, we are going to specifically look at some select statements and see how we can play around with it and try to understand it even more. Now, if I go back to my flowchart that I have here, so we've already looked at basic querying techniques, basic SQL syntax, and other things. And we look at some fundamental SQL operations now in this section, like select statement, where filtering and ordering and so on. And then we'll move on to other topics as well within this. So if I jump back into my BigQuery, we already have an employee table over here. Let's first go in and delete this. So I'll just say delete, and that gets deleted. And I'll come into my, and I'll copy this from my notes over here and then go back and paste it in here. Again, this is the data set, which is the SQL. And we're creating a table called employees, where we have employee ID, which is an integer, name, which is a string, age, which is another integer, and department, which is another string as well. So if I run this, that gets created. Now, let's insert some data into that table. So let me just copy this from my notes, go back, and let me just paste this here. So let's change this data set to SQL. So we are saying insert into this table employee ID, name, age, department, which is the order of data that we're giving. So we'll say the values are one, which would be employee ID, Alice would be the name, 30 is the age, and department is HR, and the same thing for other people as well. So at the end of this, we'll have three records. So instead of pressing the run button, you can also do command run on Mac, and that should also run the query. And now we see that we have some data here. So if I click into this table and go into the preview, so we should see all the data that we have. So let's start running a few more select queries just to get our understanding a bit deeper. So the first query we want to run is select name and department from. So we want to first select the name and department, which is just that. So I like to put the from on the second line. And then we have it something like this, where we have select name department from SQL.employees. And we should get two rows of data, actually all the rows of data because we're not limiting anything. And we have all the names and departments that the employees are part of. We can also do select star if we want to get all the columns, right? So if I do select star, this will give us all the columns like the employee ID, name, age, and department. And if we do this, where we can add a condition. Now imagine this is our table where we have Alice, Bob, and Charlie and their departments. And if we wanted to get just the IT department, then we can do that as well. So I'm just going to copy this, paste it in here. So we have SQL.employees where department is IT, and I can press this run button, and then we should get Bob and the age. Again, if I do a star on this, we should be getting all the columns. So there we have it. We have a simple select query over here and then a where clause, and we can start adding more to this where clause as well. So imagine, let's comment this line out and let's go back to the data again. And let's say we want to also, let's say we want to add another condition over here. So let's say age is greater than 28 and department is IT. So this is how you would add multiple filters or where clauses within a single SQL query. Let's also run a few more where clauses to understand filtering the table a bit better. So we'll keep working with the same table that we have in BigQuery, but some of the operators that we can use within this where clause are right over here. So we can use equals, not equals, greater than, less than, or greater than equal to, less than equal to. Like and in are something that will make sense when we start running these queries. But yeah, these are all the operators that we can run, and there's more as well. So let's start by looking at this statement over here. So instead of running this, let me just explain this first as well, because we've already run this. So here we are filtering by the department called IT, and then we can also do a greater than, which gives us age greater than 30 from this table. And this is where it gets more interesting, where we can do some pattern matching as well. So here we have a pattern where we are saying name like A and then percentage. So anything that starts with an A and then percentage is just catch all. Anything that comes after this is still fine. So it'll match anything that starts with an A and then give all the employees data over there. So let's just copy this part only. And then let me just go back to BigQuery and then we'll see how this shows up. So we have select star SQL employees table where name like A. So if I run this, let's see what we get. We have only Alice over here. Let me just comment this section out. So, and then bring in, let's insert some more data into our table. So change this to SQL again, and then hit run. So in total, we should have 6 rows now. So if I go back and uncomment this, and now if I run this, we should have at least 2 rows of data, which is Alice and Alice1, right? So anything that comes after A, it gets or catch all, but then it matches A and does that. So if I just do B, we get Bob and Bob2. But if I do a low B, it doesn't match because this is case sensitive. So it has to match the case as well. We'll try to understand sorting features within SQL as well. So far we've understood the select statement, the from statement, and the where statement for filtering. Now we have the order by, and to actually use this, we just give it a name of the column and then specify if it's ascending or descending. And you can chain multiple sorting into the order clause by adding one more column with just a comma and then adding a few more ascending or descending. So we'll try this out within our example employees table now. So just to understand this, so we have age name, and then we can just give it order by age descending. So let me go back to this, and then we can do order by age descending. So let's see what we get here. Now we have the age sorted by descending order, where we have the greatest number over here, and then it's going to the lowest number. So that is age by descending. So we can chain multiple sorting into the order as well. So let's pick up this department ascending and then age by descending. Let's see what this does. So I'll come in here, put this and place a comma. So now we are ordering by department, right, in ascending order, and then age by descending. So remember, the department is a string, so it should be, if we are saying ascending, it should be in alphabetical order. So if I run this now, so we have they sorted by ascending, and then age should be descending. So this would really make sense if a department had multiple people in them, and then they had differing ages. So this would sort first on the department, and then if there are rows which are completely equal, then they get sorted by age. I also want to mention that if at any point you have any questions at all, do leave a comment, and also subscribe to my channel and like this video so that you're really indicating that you are benefiting from these videos, and I can think of making more of such videos in the future as well. And also in the comments, leave what are the topics you would like to learn about within data science, data engineering, data analytics, and even marketing as well. And I'll try to cover as much as possible on this channel. So far we've been running a few SQL queries with select statements, from, select, order by, limit, and so on. But there are a few functions which are very specific to BigQuery as well. And it's always good to understand all these functions, because even in other databases, there might be similar functions which are named differently or they are used differently, but always the documentation really helps there. So let's look at some of the specific functions within BigQuery. So if you look at the string functions, there is the regex extract, format, and various other regex functions as well. So this is just to give an understanding, or just to give you a flavor of what's out there. But the best place to again look for all these functions is the BigQuery documentation. So if you think about array functions, there are array aggregate, array concatenation. Again, there are various date time functions as well, and of course some geographic functions are included in BigQuery as well. So we'll take a look at some of these examples, and then try to understand them. There are also analytical functions like lead, lag, row number, and these are quite intermediate to advanced level, so we'll look at these in that particular section. And of course, there's machine learning functions within BigQuery because of BigQuery query ML capabilities. So we're not going to look at this, at least in this course. Maybe if I do an add-on course or an update to this, that might include some of these. But for now, we'll just stick to these. I try to run this and then try to understand how they're working. So again, for this, we need a data set. So we'll again create an employees data set, but this time we are going to add a few more columns like salary history, timestamp, and join date, and so on. And if you notice, they have a different data type. Actually, let me go back to the actual query we'll be using to create this table. So the employees is an integer, name is a string, email is a string, but the join date is actually a date. And there is a salary history, which is an array of integers. So imagine we have an employee whose salary changed over the course of 3 years, and for every year there's a new salary, so we want to keep track of all of that. So we can add all these salaries in an array and store it in this column. And there's also a timestamp, and this is again an array of timestamps. So this could be anything. Maybe this could be the timestamp of when the salary got changed or something along those lines. But for now, we'll just create a sample table like this, and add in this sample data as well, and see how this looks. And we are going to run some of these queries that we've just talked about. So let me just copy this, and then I'll go back into my BigQuery. Let me open this and paste this here, and this should have a data set associated to it. So sql.employees, and we'll create this table. Let me look at the next statement where we are inserting all this. So let me just copy this, expand this out, delete this, and paste it over here. And what we're doing is we are inserting into sql.employees, and we are saying that the first value that we'll give is the value of the employee ID. There's a name, There's an email, join date, salary history, and timestamp. So we're just getting an error. Let me try to look at this. So this error is saying that we are passing a string, whereas it's expecting a timestamp, because if we look at a schema, we said we are going to provide timestamp. So to fix this, we just wrap this value around the timestamps like this. So let me just copy this entire thing again and go back to here and change this to SQL dataset, and this should fix everything, and then we'll insert this data into our table. Let's also run a select statement to see what kind of data we have. So we have employee name, email address, join date, and salary history is actually an array. And this is how BigQuery displays it. It's an array, and then we have some timestamp arrays as well. So if I just select these two columns and then look at this, so this is how the data looks like. So we have an array of salary history and then some timestamps as well. So let's try to run the BigQuery specific functions that we had and then see what we can understand from them. So we have regex extract. So extract the domain from the email address. So if we do a regex, and if you're familiar with regular expressions, you can understand what is this doing. So we are saying from at we want to get all the characters. So let me copy this and go over to this function and then go to my BigQuery and paste it in here. And don't forget to add the data set. Now, if we run this, we should get the domain. And if we look at what was the initial value, so if I come in and look at the preview, let's see what the email was. So the email was johndoe@example.com. And because we ran this regular expression, now we are getting only the domain. We can also print the email as it is. So if we run this now, we'll also see the email and the part that was discarded after the at. So this is regular expression. So next we have the format function, where we can format the name and employee ID into a single string as a formatted name. So let's see how this looks. So if I copy this over, so now we have a formatted name in the format that we have specified over here. So percentage %s is for string, so name is a string, and then we have percentage %d, which is the employee ID. Now we can add in as many types of functions we want. So if I just add some text over here and run this, this will still work, and then pick up the value over here. Now a simple way to undo all of this and get just the name and employee IDs separated by an hyphen. So we get John Doe 1 and John Smith 2. So this is the format function where you can format the text as you want, and then we can give it the values that we want to add in here as well. Next, we have the array functions, where we can manipulate the arrays as we want. Now, one thing to note when we are working with arrays is unnest, which is a very important function that we have to understand in SQL. And I know we haven't covered this in the past, but there are a few more sections in the future where we are going to cover this. So if you don't understand all this in this section, so that's still fine. You can just go through this video and understand that these do exist. So if I just have select staff from SQL employees, this is all the data we get. So we have the employee ID and name, and we know that we have salary history as an array over here. So let me simplify this. Let me just get the name and salary. Actually, it's salary history. So we have the name and the salary history, and let's try this function now where we are unnesting the salary history as salary. Let's do an unnest. Let me just paste this over here. So now we have a salary. So instead of salary history, if I remove this and then replace with salary now, so we should have multiple rows created now. So we have John Doe 70,000, and then there'll be another row for John Doe 75,000, and so on. A good way to understand what row we are on is actually this row number. So if you see here, we have one row for John Doe, and then all these are appearing in the same row. And then we have the same thing over here for Jane Smith as well. So just notice what is going to happen when I unnest this into salary, and then we have salary on its own. And if I run this now, so we have more rows created, but for each row, we have unique salary values. Now we have 3 John Doe rows and then 3 Jane Smith rows with all the salaries appended here. Now, again, you don't have to really understand this because we'll have more a visual way of learning unnesting and so on. But this is just a quick intro to how unnesting of an array works. Now, let's go and do array aggregate of salary and see what we get over here. Now, when we're doing array aggregate, if I just paste this over here, you can see there's an array being displayed by BigQuery, because array aggregate is an aggregate function, and we really have to group by or use aggregate functions to use this properly. So again, this is coming in a future section, but for now, we'll just remove all of this. Now, what this is going to give us is it's going to give us all the unique values from the salary column over here. And if I run this now, we just get all the salaries across the company. So we just have one row, and then this is creating another array of all these values. So that is what array aggregate does. It is an aggregate function where it takes all the values that it gets and then creates another array of values. So we can know that this is an array because it's just one row. If it had multiple row numbers, then these would be multiple row values, in which case it wouldn't be an aggregate. So we know that this is an aggregate because there's only one row over here. So similar to an array aggregate, there is another function called array concat, and there are many other functions as well on arrays specific in BigQuery. So we can look at all of those, but this is a bit more again intermediate advanced query where we have subqueries over here, and then we are running an array concat. Let's just run this for the sake of understanding and to challenge ourselves. And when I run this, we get a combined salary list like this from all the employees. And if you want to understand this at a very high level, we have this query over here, and then we have this query over here, and then the results of these two queries are provided to this function, and then that is appearing as combined salaries. So if we were to just take this example over here where we have salary history from employee, and then we are selecting employee 1, then we would just get all the salary history array there, and then we have another array appearing from employee ID 2, and then it gets concatenated. And we look at this function in a much more detail in later down the series. So going back to some of the simpler functions, we have time functions, which are very interesting. So we have time difference, and we can get the number of days difference. So let's just copy this and try to run this on our data set. Now here, what we're doing is we are doing a select name, and then there is a time function and a current timestamp here. So current timestamp gives you the current timestamp of the current time in BigQuery. And then there is this timestamp ordinal 1. And to understand what's happening here, let's go back to the table. So we know that this timestamp is actually an array of multiple values, right? So if we just wanted to get the first value out of this, we would say ordinal 1. And then if you want to get the second value out of here, it's just like an array, accessing an array in any programming languages, you would say 1. Sorry, if you want to access this value, that would be ordinal 2. So if we change this to 2, that would be ordinal 2. So all we're doing here is we are getting the first value, this timestamp, and then we are subtracting this timestamp from the current timestamp or today's date, and this will give us the value of the number of days over here. So if we look at this, if I run this now, we have John Doe and tenure days. So let's also print this current timestamp to see what we are getting. So I'll just put the current timestamp over there. And also let's look at what this timestamp ordinal value is. And if I run this now, we've just added 2 more columns. So let's see what we get. So we have this, which is the current timestamp over here, which is 2023 today. And then we have the timestamp ordinal, which is what we have here, which is 2020. And then there should be one for Jane Smith in 2019, right? And we are getting a difference of this value minus this value in terms of number of days. So we can also change this to, instead of a day, we can look at the number of hours between these two dates, and we would get the tenure hours, right? So this is looking at timestamp difference, where we give it one timestamp and then we give it another timestamp, and then we get a difference. Then finally, we also have a date trunk. So truncate the join date to the first date of the year. So let's run this. So let's look at what we have here. So we have the join date. So this is 15th of January 2020, and then this is 10th of June 2019. So if we want to get the first day of this month, instead of 15th, we would get the result 1st of January and then 1st of January here again, because we are doing a date trunk for year. Now we can change this also to a month. So instead of going all the way to January of 2020 and January of 2019, we would get the relevant months as well. So if I run this now, we can see that we have 1st of this month and then 1st of June as well. So this is date trunc, which we are truncating the date to the start of the month or the start of the year, and so on. Now, the next function that is also very interesting in BigQuery is the geographical data, and then we can do quite a few things like calculating distance between two locations and so on. So if ever you have location data within your BigQuery, you can run all these queries. So for this, let's create a separate table called geographical data where we give it a name and a location. And notice the data type over here. So far we had int, boolean, string, and so on. This is a new data type within BigQuery where we are saying it's a geography data type. And if you notice the data that we're loading, so we are saying insert into geographical data, which is the same table over here. We are saying the name will be location one, and the location itself, which is expecting a geography data type, we are giving it geopoints. So these are the latitude and longitude of the location, and then we give it over here. So let's just try to run this and see what we get. Let me jump back into BigQuery. So I'll change this over to SQL. And if I run this now, there should be a new table created, right? So there's a new table created. Now let's try to insert these values into that table. Here again, change the data set to SQL and run this, right? So new two rows of data have been inserted. Let's just give it a quick look. So if I open up the table that we just created, we have the type geography here for the location. And if we hit preview button, we have the location, which is latitude and longitude over here. So let's run the distance query to understand what queries we can run here. So if you want to calculate the distance between this point and some other location or this point or some other location, you can do that by using st underscore distance. So here we give it the location, which would be either this or this, and we give it another point in the world with latitude and longitude, and then it'll give us the distance to that place, right? So if we click on this and then go in here and let me try to run this, and don't forget to change this to SQL, the dataset name, and then let's look at what kind of data we get now. So we have location one, and then the distance to downtown, which is the location that we've given here, is this, and this for location two as well. So that's a quick introduction to geography function. And of course, there are many other functions within this as well. Again, the best place for all this is documentation. Let's just open that up. So if we search for query syntax BigQuery in Google or come to this URL, we should have a list of all the things that we can run within BigQuery. So there are all these functions which we haven't even touched on, but it's all here. And you can go through all of this and understand this a bit better and try to find if there are other new functions that we haven't spoken about, because these things are always getting updated. And finally, in this section, let's also look at how we can import and export data into BigQuery. And this is very specific to BigQuery itself. And although this is an SQL course, I just wanted to introduce you to this. And this would be useful when we want to load data and so on. So we have various ways of loading data into BigQuery. So the first option is, of course, looking at cloud storage. We can just dump a CSV file there. And then if we use this query, this will load the data into BigQuery. There's another way of doing things, which is using streaming data. So this will happen in real time. If you're using like PubSub or Dataflow and other services within Google Cloud, again, those are out of scope of learning SQL, and it's really not required. There are also ways of just loading from other Google services like Google Sheets or Google Ads and Google Drive as well. And there are federated data sources as well, which means that the data still lives in an external data source, but we are just using BigQuery to run SQL query on those data sources as well. So if we want to load data, we can try this, where we dump a CSV file over here and then this loads the data in. And similarly, we can also do an export of data as well, where we specify we want to export data with destination format, give it a format of CSV, and then we give it the Google storage bucket name and then the file name, and then we give it the data set and the table, and this exports that file into a CSV. There is also a handy function within here as well. So if I go to this and if I run a query in new tab, and if I just say select star, so if you want to download this data, you can come in here and save results, and you can download it directly from the browser. So this will save to Google Drive, or if you want to do it local copy, you can do that as well. So those are some of the ways you can export data out of BigQuery. So in this section, we are going to be looking at manipulating data block of this flowchart. Now we do have a few more before we finish off the beginner section and then move on to the intermediate and the advanced section. Right. So let's jump into my notes and then see what we are looking at now. So the first one we want to look at is this insert statement. And we've already been doing some of these insert statements already, but this section gives us a chance to look into this into a bit more detail and understand the proper syntax of how to go about using this. So insert statement allows us to add new rows of data to a table when we are writing SQL. And there are two ways of doing an insert. The first one is where we specify all the column names and give all the values. And the second one is you can just leave out all the column names and just start inserting the value. But with this, we have to make sure that we are giving all the values that the table expects or that we've defined in the schema, right? So let's take an example and see how this actually works. So imagine we have this table over here that we've created with employee name, age, and department. Now, when we do an insert into, we can give it all the names of the columns that we want and then give the appropriate data in here or the values. Or if you want, we can completely get rid of this section if we are sure that we are giving all the values for all these columns. Now, in this particular example, it doesn't make much of a difference, but imagine if this table had like 10 columns or 50 columns and you don't want to give all the values to those 50 columns, then you can just define all the columns that you're giving value for. But for a smaller table like this, you can keep this or discard it. Now let's quickly run this example in BigQuery and see how this works. So let me just copy this and then jump back to BigQuery. So in here, let me paste this. So I'll also call this employees underscore two and then change this to our SQL. Now we are creating employees underscore two with all these values. So let's just run this and that should appear here in the sidebar. Actually, let me collapse this because we don't really need that navigation. Now let me try to add some data into that by copying this, right? So what we are doing is we are inserting into SQL data set and employees two table, and then we give it all the column names that we are giving values for, and then we give it all the actual values, right? So if I run this, oops, I have to run it now, right? So we have three values that's added. So if we want, we can check all that by running a simple select statement. So if we select this, it'll only run this block in SQL, and we have some data here. Now let's also try running this without giving any of these column names. Select this block and then run. Right here, we're not giving all the column names, but we are still passing all the values that the schema of this table expects. So this value is valid. Now, if we run this again, where we select all the tables, now we have all the values like Alice 4 and Alice 5 and so on. Now let's also try something different and let's skip giving some of these values and let's see what happens here. Now right away you can see we have an error that's showed up. So inserting row has wrong columns and BigQuery is already complaining, right? So if I just look at the schema that we defined now, even though these are nullable, BigQuery is not liking it. So, but if we specify the column names, let's check if this works. So I've just selected all of this and let's also change this to 6 and then Alice 6. Let's do that and then run this now. So now we see that employee was added even though we didn't give all the values, but we selected the column names that we were giving values for. And finally, if I run this, there should be Alice 6 and the other two, age and null, age and department will be null because we didn't pass the value for that. So that's just a quick intro into how we can use the insert statement in SQL to insert data into BigQuery. Next, we have the update statement. And as the name suggests, it is used for updating a value in the table. Now let's just quickly understand how the syntax works here. So we first have to write the update syntax function name and then give the table name, and then we write the set function name and then give it the column name and the value that we want. And we can also filter by a condition here. So again, There's a table name, there's a set which specifies the columns to be updated to their new values, and then where is used for filtering the data. So if we take a quick example over here, so we have the update and then we are updating the employees table, and we're setting the department, which is the column name within the table, to this string value, and then we are filtering only to employee ID equals 2, right? So let's quickly run this and see what happens. Now, this is the insert statement that we had before. So let me just make some space over here and then write this. So we'll also change this to SQL dataset and then change the table name to employees underscore two. And where we see Bob over here is assigned to department ID. Let's run this and see if Bob gets assigned development department. So when I run that, I can do a select star from table, and let's look at the ID number 2, Bob, and sure enough the department has been updated to development. Next we have the delete statement, and as the name suggests, it's used for deleting values from the table when a certain condition is met. So the syntax goes delete from the table name and then give it a filter, right? Let's look at a quick example here. So we have delete from employees table, and if you want to delete everyone in the marketing department, we can do that. So let's just copy this and go over to BigQuery and run this now. So I'll just make some space over here. So we have delete from SQL dataset, and this is our table. So let's say we want to delete everyone where department is marketing. So that is only Charlie ID number 3. Let's select this and run, and that value is deleted now. So let's check. So number 3, Charlie, should be gone. Yeah, sure enough, it's gone. So you can also, department is null if you want to do a data cleanup, and then you notice some of the values are null, and that's affecting your analysis and you want to get rid of those. So you can just remove that by saying is null. Okay, so that row is removed now. And if I bring up all the rows, we should not have that null row that we had created. So that's a simple way of deleting some rows from table using SQL. Let's start looking at some basic querying techniques, and we are really close to closing off some of the beginner section over here. So the first thing that we have in this basic querying technique section is to use some aggregation. So aggregation really allows us to perform some calculations, and in return we get one single value out of our SQL query. And some of the most common ones are over here. We have the count, we have the sum, and we have the average. And as the name implies, those are some of the mathematical functions that we are going to get values. The syntax for this is exactly the same as we have been running some of the queries, but the only difference being we provide it a new aggregate function name and a column name to go along with it. And as an example, let's take a look at this data set where we have the product ID, the quantities, and the sale amount, which would correspond to this, the product IDs, the quantity sold, and the sale amount. Now, if you wanted to get count of all the sale orders that you have in this table, you can just run a count on this and we would get the values. And we have some example over here where if we run the count star, star just means it can be any column. We just it's like a wildcard. Instead of specifying a column name, we just give it a star and then everything picks up automatically. So we have count star and that gives the count. If you want to do a summation, the sale amount, we can do that, and that would be like the total revenue. And we can also get an average of all the sale amount called the average sale. So let's quickly run this within BigQuery. So I'll just create that table. Actually, I just need to change this to my data set, and let me insert values into that table. And let's run the total number of sales query. I'll just format this, or you can come into more and then click on format query, which formats it for you. And let's do sql.sales. One thing you might also notice that we haven't seen so far is this as and total sales. So this is not really necessary, so you can remove that, but that will remove the custom name that you're giving to the column for when the output is generated. So if we run this as is, then you'll see that BigQuery creates a pseudo column name for us. But if we are not happy with that, we can give it any name that we like. and that should appear as the column name. We can also do sum on sales and average on the sales as well. So let's do sum on the sale amount and run this. So we'll get total revenue, and if we do an average, we should be able to get the average revenue. So those are some really quick aggregate functions, and next we'll look at some grouping and other complicated stuff. Next we have one of the most commonly used clauses within SQL, which is the group by clause. And group by clause is widely used because it can group rows that have the same value specified in the columns into summary rows. So for example, if you want to find the number of customers in each country, then you would run a group by clause. Even that was a bit confusing. So let's just look at a table of data, and this makes much more sense. So imagine we have the region and the sale amount. So we have all the regions and we have all the sale amount. And if you wanted to find out what would be the sale amount for each of the regions, that is when you would use a group by. If you don't want to group by the region, and if you just wanted to get the total sale amount, like in the previous section, you can just run some sale amount and then that would give us the result. But in this case, we want to get actual values of these, and then that should be aggregated. So if you see here, we have east here and here. So when we run the summation, we should get 300 plus 150. So let's run this in BigQuery and try to understand this a bit more. So I'll just copy this over. So let me just call this sales underscore 2. We have region and sales, and let's insert some test data into that. So this is SQL underscore 2 and this is SQL, and we have all the data in here. And let's run the actual query where we are giving it the aggregation and we are also giving the group by clause. So the summation function takes in the value of the column that we want to sum, and then the group by takes in the column name which we want to group by. So if I just copy this, and this would be SQL, this is sales underscore 2, and we have an error here, so that should be select, and this should give us all the regions and the total sales in those particular regions. So now you see in east we have 450 sales. This is how you would do a very simple group by the region, and this is widely used across so many different queries that you'll come across in real world. Again, this is an alias as total sales, so you can change this to anything you want, and that is just naming the final column after the sale. Right now let's also try to remove this and see if this runs, because we should also know when we can use this and what are the conditions that we can use this. So if I run this, this will still run and then give us all the result. If I comment this out and run this now, it has 4 values, but because we were doing a group by, it gave us group by with all the results. So that's a simple example of doing group by. We'll see more complicated results when we actually do get to do some complicated project stuff, but this is very simple introduction. The next clause is as important as the group by clause as well, and this is called as the having clause. So this is for filtering after we've done a group by, right? So that's a very simple way of looking at this, because we already have a filter where we are filtering the data using the where clause. Now we also have another clause over here which is called as having clause, and this is also used for filtering. So a very simple way of thinking this is this filters all the data that we have here, and where is used before the group by, and having is used after the group by, right? So once the grouping is done, then if we want to filter on that result, then we do the having clause, right? So a simple example, again, we've already run this in our previous section, so let's also run this and see what kind of result we get. So I'll put back my group by and also this, and let's also bring in the sale, total sale amount as total sale. And before I run this, let me just run this query without the having clause, and then we'll run it with the having clause. So right now we have grouped all our results and we have east, northwest, and all these values. If you wanted to get only the rows where the total sale was greater than 300, so you would put in this filter and run this, and now you would get only the values of the rows where the value was greater than 300. Again, this is a filter which comes after group by. So once you've done group by, you can filter the values again and get your desired table. As we are progressing through learning more and more about SQL, I also want to touch upon the topic of performance and large data sets and how to handle those and how to get the best performance when we're running these large SQL queries on these large data sets. So there are quite a few techniques that we can use. And first and foremost, we have the partitioning and the clustering, which is a way of partitioning the table into smaller tables, and clustering is grouping values within that partition. The first strategy for improving performance or working with large tables is to use partitioning and clustering to organize the data in the table. So partitioning splits the table into segments based on a specified column, like a date or a timestamp. And clustering sorts the data based on the contents of a selected column. And this is useful by the type of queries that we are running. So let's take a quick visual example of how this looks like. So I found this on Google, and this seems to give us a good starting point to understand partitioning and clustering. So imagine this is our starting table, and let's imagine this is like petabytes in size, and we don't want to run queries on this huge table because that will reduce our performance and bump up the cost as well. So we can partition this table by the date column. And if we are running more and more queries based on the dates, then this really helps because we are splitting it into different smaller tables, and this improves our performance quite a lot. So when we partition this by dates, so we have all one dates in one partition, and then this is another partition, and this is another partition, and BigQuery knows where to exactly go and get these values because they're all partitioned and stored together. Now, the clustering also happens when we want to not only partition the table, but also want to group the similar rows together. So we have Android and Android together. So if you're running group by or more queries where you're looking at just Android, then this increases the performance quite a lot because you've clustered this table around these tags as well. So similarly over here, we have all the Androids together. And when you give a group by to look at all the tags where it's only Android and this particular date, so Google exactly knows, or the database exactly knows where to go to get these, and the performance increases because it doesn't have to search through this or this cluster or partition. It just has to go and get data from this partition. So that is one way of improving performance by partitioning and clustering. And we'll see some practical examples later on. But in this section, let's just understand what are the other techniques that we can use. The other ones are optimize query performance using not using star all the time. So instead, specify only the needed columns, because we've already seen BigQuery is a columnar data storage. So if we specify only the columns, then that increases performance quite a lot. And we can also get approximate aggregations, like using functions like approx, count, distinct. And this gives approximate results which are at least closer to what is reality. And we can use this when the exact results are not necessary. And we can also leverage power of window functions for complex calculations. So we haven't touched upon window calculations. These aggregations come in the advanced section, so we'll wait for that. We can also manage the data scans and cost. We have to be mindful because BigQuery charges on the amount of data that is processed. So the more we can use this where clause to filter out all the data that's not necessary, and the more we can use the limit clause, and the more we can use specify the exact columns they are interested in, the better our query performance will be. Next, we also have external data storage that we can query from. And this is really good if the data is in cloud storage and if you just want to run some infrequent SQL queries. So that is good on BigQuery. There is also caching of results for repeated queries. So BigQuery automatically caches results for 24 hours. So if you reuse the same query, then you'll get the result from the cache. We are nearly finishing the beginner section, and we have join tables and the basic database design. So we look at this exciting joining tables. In relational databases, data is generally stored in various tables. So for example, if you're looking at e-commerce, sales data might be separate table, orders data might be separate table, customers data might be separate table, and so on. And to get any meaningful analysis done out of all these tables, we usually use joins to blend these tables together and then make it into one big table that we can run queries on. So there are various types of joins that we can do if we have multiple tables. So there are inner join, left join, right join, full out join, and so on. But in this section, we look at inner join, left join, and right join as beginners, and we look at more complex joins a bit later on. Now, I did find a good visual for this as well that might help us in conceptualizing or keeping this in our heads when we come across all these joins. So first of all, we have the right join. So imagine table A is on the left and table B is on the right over here. And when we do a left join, all the values from table A stays intact. So one way to look at this is that all these blue circles have all the values intact in them. We don't miss out on any values there. So in this A, if this is our A table and this is our B table, and if we are doing a left join on this, all the values in A remains in the result. And if we look at similarly on the right join, all the results in the B remains and A might not have all the results, and so on. So this is a quick visual, but then let's jump into each one of them in detail and try to understand them. So let's first look at inner join. Inner join in SQL is used to combine rows from two or more tables based on a related column, and it returns only the rows where at least one match in both the tables. So this is the key here, at least one match in both the tables. And the basic syntax of this is the select from, which we've already seen. And then these are the two new lines that we have when we look at joins. So we are saying in a join table 2. So this is all the query for table 1, right? We are selecting the columns and the table 1. Now we say inner join table 2, and then we want to give it on what would be the common key or the common value between these two tables so that these rows between these two tables can be matched. And that is what is defined over here. We say table1 dot common column equals table2 dot common column, and that would give us the join. Let's look at the table, which will make it a bit more easy to understand. So here we have the employee table and the department table. Now in the employee table, we have this column called department ID, and we have all the department IDs over here. And in the departments table, we have the department ID and the department name. Now imagine you've been asked to do an analysis on the names of people and their department. So we won't be able to run queries on this single table itself because we are missing all the department names over here. So this is a good situation when we can do a join on this and then get all the departments. And a good way to run in a join is we already know the select from, so we can run through this. So we give it e.name and d.department. So you might be wondering where these e and d are coming. So these are called aliases. So when we say from dataset.employees, we say EO here, and this becomes the table name now, which we can reference in our query selecting columns and such. And we do the same for the dataset dot departments table where we give it an alias of D. So we are saying we want the name of the employee from the first employee table, and we want the department name from the second table, and we are joining it on the department ID because that is the common column that we have in both these tables. So let's walk through this and see what exactly happens when BigQuery encounters this query that we've given it. So we first look at one employee ID number 1, we have Alice and department 101. And when we are doing an inner join, the values in both table must exist. So we are looking at 101 over here and 101. So we have those values. So this row gets appended to here, and we have all these columns here. Next, so if you go to the next row, we have employee 2, Bob, and we have 102. So we have 102 in here as well. So this is good. It's a match. So now that comes into here as well. And let's look at the third example in this inner join. So we have Charlie. He is in the department 103. Now there is no 103 in this table. There's only 104. So we won't be getting the result back for this row. So we'll only get these two rows as our final result. So that's how inner join works. Both the columns must have all the values, and only then we get the result back. For values which are not available, like 104 finance is not here and 103 is not here, those rows get discarded. Let's quickly run this in BigQuery and see what we get. So we have the create statements for both the employees and the departments table, and we'll also insert those values. So let me just select this and create this table, and let me create the department table. Let's insert some values into employees table, and we'll also insert some values into the department table. Let's run the inner join query now. So to run the inner join, so let's do a select statement on our SQL employees, and this is what we've run so far, so that's straightforward. Now if we also bring in the inner join where we are joining on the department ID, so E is the alias for employees table, D is the alias for department, and we can also bring in the D dot name. And if we run this now, as we see, we only get 2 rows, but in reality, if we check the employees table, we have 3 rows of data, and similarly in department, we also have 3 rows of data. But because we are doing an inner join, both the values for department ID must exist in both the tables for it to appear in our final result. So that's inner join. Left join is quite simple as well. So when we do a left join, it returns all the rows from the left table and all the matched rows from the right table. And if there is a no match, it just returns a null. And the query and the syntax is very similar to the inner join that we just looked at. So we just specify the type of join we're doing, and we also specify the column, which should be the key or the common column between the two tables. So let's run this in BigQuery and try to understand this a bit more. So we already did inner join in the previous section. So now let's change this over to left join. So now what we expect is we expect all the rows from the left table, which is the employees, and then this the department is the right table. So we're expecting all the rows from employees table to be present in our result, only the matched rows from the department table to be present in the result as well. So if we take this example to understand this conceptually first, so we first have 101 for Alice, so we find that value over here, and this value comes in here, right? So we have all these columns, which are all the matched columns from this table. Next, we have 102 for Bob, and we have a match here, so that is good. We also get this value over here. Next, we have 103, and we don't have that 103 over here, but because we are doing a left join, we will be retaining all the rows over here. So there will be no join on this row, but then this will be just left as a null row or an empty row, right? So this is what we're expecting. Let's run this query and see if we get the same result. So now when we run this, we see that Alice, Charlie, and Bob, all the people from our left table, which is the employees. So if I go here, Alice, Charlie, and Bob, they're all there. Where we are missing value is Charlie over here, where the name is null. Actually, let me change this to as department name so it's a bit more readable. So we have Charlie, whose department is null. So in here we don't have 104, and Charlie's department ID was 104, and that is missing. So when we did a left join, all the values from the left table are retained, and only the matched values from the B table are retained, and anything else is just left as null value, like we see here. Similarly, we can work through the right join as well. So in a right join situation, all the rows from the right join are available in the result, and only the matched rows from the left table are results. Although in real world, right join is not that common, because usually you can get the same result doing a left join as well. But it's good to know that right join also exists. A visual for this is right join, all the rows from the right table are returned in the results, and only the matched rows in the first table. So if we just change this to a right join, and let's see what result we get here. So we see all the data from the department table is present over here, and only the matched rows from the employee table are present over here. So again, right join is all the values on the right table are here, and this would be the left table, and only the matched rows are there. So if you were to work through this example over here. So this would be the right table. So all these values are retained and only the matched rows from here are brought in here. So 101 exists, so that comes in here, and 102 exists as well, so that will come here, and 104, there's no value over here, so this will be a null value, which is what we are seeing here. So we are almost done with the fundamental SQL operations at this point, and let's look at the basic database design section, and then we can move on to the intermediate and advanced sections. So the first topic within the basic database design is all about normalization. So normalization in database design, it's a process of organizing data to minimize redundancy and dependency. And this usually involves dividing a large table into smaller manageable ones and defining relationships between them. And this is really good for performance, but it also increases the number of joins and other things that we have to do. But let's look at this in a bit more detail. So what are the goals of normalization? It's to eliminate redundant data, so to avoid duplication, to reduce storage and so on, and also minimize data modification issues. So when the table is very simple, then it's easy to modify it, where you don't have to think too much when you're doing insertion, deletion, or updating that particular table. And this will make more sense when we look at a practical example. And it also increases the data integrity, where we can ensure data consistency defined through relationships as well. Before we look at each stages in the normalization, let's just jump into a quick table example. So imagine this is our table where we have the employee ID, name, department, and department location. So this is a good table, but it has a few issues. So the first one being it has this redundant data called department location. And this table has multiple pieces of information like the department, department location, and so on. And if we think about this, it's not really easy to maintain such a table where we have multiple pieces of information. Now, although in this particular instance, it's very simple table, it's very easy to maintain, but imagine if this table had a few more columns and a few more rows and it was a large table, then it becomes quite difficult to maintain the integrity of all this data. And that is where we use normalization techniques. So there are three stages to normalization. So there is the first normal form, there is the second normal form, and the third normal form. So the first normal form ensures that each column in the table is atomic and each row is unique. So when I say atomic, it just means that each column just has one piece of information. So it doesn't include like JSON data or like an array of data or multiple values of data within each column. So it has to be atomic, just one piece of value within it. And the second normal form is when it meets all the requirements of the first normal form, which is the column being atomic, and removes subset of data that applies to multiple columns and places them in separate tables. So all this means is, if I do have a note over here where we can remove this department location from this table and put it in a separate table and create an entity relationship between this table and the other table. So if we take the example of this table again, so if we were to apply the two normal form here, we would end up with two tables like this, where the first table has employee name, employee ID, and department ID now, instead of the department location and the department name itself. And then we have another table called department, where we have the name of the department and its location. So this is the second normal form, where we've split one big table like this into two smaller tables. Like I said, normalization is very good, but it also comes with the downside that you have to do a lot of joins to get to the table that you're interested in querying. And there is the final third normal form as well, which meets all the requirements of the second normal form and removes columns that are not directly dependent on the primary key, which means in this case we have employee ID, which is the primary key, And in these two tables, we have the employee ID primary key and the department ID, which is the primary key. So when we do the third normal form, any columns that don't directly depend on this primary key are removed. And if we had extra columns, let's say which did not add value to this department table, or which did not depend on the primary key of this table, those would be removed, and that would be third normal form. Next topic within the basic database design is all about designing simple tables. So we always want tables to be simple and well structured, but also that reduces complexity when we are querying it. So we have to ensure that the table or our design of the database is efficient, scalable, and it's easy to maintain. And the goal is to create tables that accurately represent the data but avoids unnecessary complexity. So there are a few key principles that you can think of. So ensure that it has a clear purpose. So each table should have a clear purpose and store data about one specific entity or a concept like customers and orders. Again, we'll look at an example in a second. Next, it should have a primary key. So each table should have a primary key that identifies each row, and it should be atomic. So just like what we saw with the first normal form when we looked at normalization, each column has to be atomic, meaning it cannot be broken down further. Like if we cannot have like arrays or multiple values within each column which can be broken down into several other columns and so on, so you have to have it in a way that it cannot be broken down, and that adheres to the first normal form. And we also have to make sure that we avoid redundancy and avoid data that could lead to inconsistencies, and related data should be separated into different tables linked with a foreign key. Right. Then there's also use of appropriate data types, which makes sense. You have to have a proper data type and ensure that it has a good schema, so that we can ensure the data integrity and optimize the storage. Now let's take a quick example to understand this. So imagine if we had a customers table, and if we are storing all the data about the customers and the order information combined into one big table, that adds a lot of complexity. So a simple way would be to separate all the customers table and orders table, and that would give us a good design. And if you think about just the orders table, if it's combined with all the customer information, now all that information is actually not required if we are just looking for the orders data. So if we consider that example, instead of having all these combined, so what we can have is now a customer ID here and a customer ID here in the orders table, and we can easily do a join on these two tables to get our desired result. But this also ensures that whenever we want to do any update, delete, or any other operations on the customer table, then we can directly do it on here. Whereas here you have to think about all the other consequences of having to update the order data or the amount and other things which are which adds to the complexity. Finally, let's also look at some cost optimization techniques, and this is very specific to BigQuery. So cost optimization is definitely very crucial when it comes to using BigQuery, and efficient design not only improves performance but also it reduces the operational cost. So let's look at a few techniques that we can use. So the first is of course efficient schema design. So design tables with only necessary fields and reduce the data storage cost, and use appropriate data types like int and string and so on, which makes sense if you think about it. So that would be the first key technique, would be to ensure the table is properly designed. So instead of dumping all the data into, let's say, a JSON type or a record type, you can add proper schema and create a table which is much easier for the storage and querying. Next is, of course, partitioning and clustering. So if this was a huge table and it takes a lot of time for our queries to run, so we can do partitioning where we split this table into different smaller chunks based on, let's say, the date column over here. And whenever we query BigQuery for that particular date, it exactly knows where to go and get that data from. So this would be partitioning. And if we also wanted to do clustering, or if our operations mainly consist of grouping by certain types of columns, let's say we have a product type over here and we know that we'll be querying by date and the product type. So we can have the table clustered so that these products are ordered in a certain fashion. So BigQuery knows to go to this partition to get the data, but it also knows that where in this partition this product or this cluster is stored. So clustering is all about just ordering based on one or more columns. And of course, then we have a way to avoid unnecessary and redundant data by normalizing tables and eliminating redundant data that we've already seen. And one other thing that we haven't touched upon so far is actually materialized view. We've seen that BigQuery caches data for like 24 hours. So if you send repeated SQL queries, it gets the data from the cache. So imagine if you're running a big SQL operation and you wanted to have, where if it's taking too long, you can have intermediary materialized view. So instead of running it on the original big table, you have materialized tables intermediaries, which you can run queries on, which will make it a bit more faster. And there is also monitoring and adjusting queries as well, where you can regularly monitor the query performance and the cost, because usually in BigQuery, somewhere in the UI, it'll actually say how many bytes scanned, and you can look at that and optimize your query by limiting number of columns or the limiting number of rows and so on. So that would be another technique. So these are some of the techniques that we can use. So as a simple example, let's say we have a sales table before optimization contains redundant data and it is unpartitioned and larger data types than necessary. So you have all these values which are coming in and sitting as strings. So they don't have proper schema defined. So a good way to optimize this is to partition by the sale date. So we have the sale date over here. Instead of leaving it as a string, we convert that to a date and then partition it by this column. And similar to what we saw, it's just going to split the table into smaller chunks that BigQuery can accurately query. And we also use appropriate data types like float and date and so on. And this would be an optimized table. So that is the end of the beginner section. And I hope you've learned something today. And wait for my other parts where we will look at the intermediate section in a separate part and also the advanced section in a separate part as well. And until then, if you enjoyed this video, like this video, and if you found my channel useful, subscribe to my channel, and of course leave a comment with any of these topics that you want me to cover in the future, like databases, data science, data analytics, data engineering, and I'll do my best to try to simplify all these concepts as simple as possible.